Welcome back. So, we're now going to have lecture number 23, which is entitled The Ideal Gas Law and the Laws of Thermodynamics. We have been talking a lot about how heat affects things, the transfer of heat. In order to get a better understanding of what's really going on within a material, within a sample of a material, we're going to take a look at the material kind of on a microscopic level. We're going to look at things kind of on a very small scale. Well, to do that, we're going to need a new mass unit. And that mass unit is called the atomic mass unit, which we will shorten to just an AMU. AMU, standing for atomic mass unit. It's a very, very small mass. 1 AMU is 1.6605 times 10 to the minus 27 kilograms. So that is extremely small. It is defined as 1/12 the mass of a single particular kind of atom, and that atom is called a carbon-12 atom. It's a particular isotope of carbon that's got 6 protons, 6 neutrons. So that nucleus with the electrons, 1/12 of the mass of that atom, that is defined as 1 AMU. We also are going to be using another number, a new number, called the mole. Now, if you've ever had any chemistry, you've probably seen this before. A mole is defined as 6.0, well, this is actually experimentally determined, 6.022 times 10 to the 23rd. And we can then convert, when we have a sample, between the number of particles, or the number of atoms or molecules, to the number of moles of those atoms. Very much like we might convert, say, numbers of eggs to numbers of dozens of eggs. So we're using the number of 12 as a dozen. 36 eggs would be 3 dozen. So we can talk about eggs as the number of eggs we have or the number of dozens of eggs. The conversion factor then would be 6.022 times 10 to the 23rd divided by a mole, and we usually write that as Na. This is sometimes referred to, often referred to, as Avogadro's number. We can then make a conversion between the number of moles of a sample, which we'll usually write with a lowercase n. That will be equal to the number of particles, which we'll write as a capital N, divided by Avogadro's number, this conversion factor. So we can convert from numbers of particles to numbers of moles of particles, just like we can convert from numbers of eggs to number of dozens of eggs by dividing the number of eggs by 12. That tells us how many dozen we have. Now, where does this come from? Where does Avogadro's number come from? Why that number and not something else? Well, it's the number of AMU in a gram. So that 6.02 times 10 to the 23rd AMU is equal to 1 gram. So by trying to determine how many of these masses are in a gram, that's where Avogadro's number comes from. Okay, very, very good. Let's take a look at some place where some of these masses are often seen, and that is in a periodic table. So here we have a periodic table that I found on a website called ptable.com, and it shows all of the different elements, and I want to take a look at just one, just for now, carbon, which is blown up over here. So on a periodic table there's usually some information very similar to this. There's the atomic number, which for carbon is 6. Now this tells us that carbon has 6 protons in the nucleus. That's why it's element number 6, or atomic number 6. It gives us the chemical symbol, which is just a single capital letter C. Tells us what the element is, carbon. And then often there's another number down here. This is sometimes referred to as the atomic weight or the atomic mass. And for carbon it is 12.011. Now what does that number mean? Well, we can think of it in 2 different ways. First, it tells us the average mass of a naturally occurring atom of carbon in atomic mass units. Now, what does that mean, a naturally occurring sample? Well, if you were to find just a naturally occurring sample of carbon, it would actually be made of a number of different isotopes. In other words, in addition to 6 protons in the nucleus, nuclei often have another particle called neutrons. And although every carbon atom has 6 protons, it can have different numbers of neutrons. It could have 6 neutrons, or 7, or 8 neutrons, for example. Those correspond to what we call different isotopes of carbon. Now, because of those other isotopes, the average mass is a little bit higher than 12. Remember, an atomic mass unit was defined as the mass of a carbon-12 atom. Well, carbon-12 is the most common isotope of carbon, but there are some amounts of carbon-13, carbon-14, but much less than the amount of carbon-12. So that presence of the carbon-13 and carbon-14 raises that average a little bit above 12, so the average value is 12.011. So that is the average mass of an atom of carbon in a naturally occurring sample. We can also think of it as the mass in grams of 1 mole of carbon. Remember, 1 mole of atomic mass units is a gram, so 1 mole of carbon atoms, if it's a naturally occurring sample of carbon, is going to have a mass of 12.011. So we can think of this as the average mass of 1 atom in a naturally occurring sample, if that's in atomic mass units. We can think of that as the mass in grams of 1 mole of naturally occurring carbon, if you were going to do a chemical experiment or something like that and wanted to know what the mass of a mole of those things would be. Okay, so there we go. And then those numbers are all different for different elements. Okay, great. Let's stick some numbers in here. Let's imagine we have 1 kilogram of a naturally occurring sample of carbon. So 1.00 kilograms of carbon. We know that 1 mole of naturally occurring sample of carbon has a mass of 12.011 grams, or 12.011 times 10 to the minus 3 kilograms. Multiplying that out, we get 83.3 moles. So 1 kilogram of carbon would correspond to 83.3 moles of atoms. Well, how many is that? What's the number? Well, we know that 1 mole is 6.022 times 10 to the 23rd particles, or atoms in this case. Multiplying that out, we get 5.01 times 10 to the 25 atoms. So 1 kilogram of carbon would correspond to about 5 times 10 to the 25 atoms. Okay, great. Now, I want to look at a particular type of material, and we're going to look at this material for the rest of the class. This kind of material is called an ideal gas. Now, we'll talk about the properties of that in just a second. The 3 phases of materials that we have been talking about up until this point are solids, liquids, and gases. A solid is basically a material where all the atoms and molecules are interacting with each other with these interatomic, intermolecular forces, and they're all basically held in place. They're all rigidly stuck where they are. They can move around their locations, they can vibrate a little bit, so to speak, but they're basically held in place by these very strong interatomic and intermolecular forces. Liquids have forces acting on each other, but they can move around and roll around each other and move relative to each other much more. So liquids are much more able to fill volumes and things like that, to stay down in the lower part of their volume and things like that. And then there's a gas. Gases have the molecules and atoms much more further apart, and they can fly around and expand to fill up whatever volume they have. We are now going to look at a gas, but a very special kind of gas. We're going to assume that the overall volume that is taken up by the gas, whatever this total volume is much, much larger than the actual volume taken up by the atoms and molecules. We're going to assume that those actually take up a negligible amount of the overall volume of the container. Another way of thinking about this is that we're going to assume that the individual atoms or molecules of the gas can have some kinetic energy. They have an energy of motion, 1/2 mv squared, but we're going to assume that they don't have any potential energy. They have no interparticle forces that would give rise to a potential energy. We're not even going to worry about gravitational potential energy for this. We're just going to assume that the particles have a kinetic energy but no potential energy. That's kind of like assuming that they're so far apart that they don't have any interacting forces between them. Okay, great. When that's true, this is what we call an ideal gas. So we're going to look at the properties of an ideal gas where we can basically assume that we only need to worry about what are the energies, the kinetic energies of the individual particles, and we don't have to worry about any potential energies. Okay, so what kind of properties do ideal gases have? Let's imagine that we've got some container with a gas in it. And let's focus down on one particular particle of this gas, one atom or maybe one molecule. Let's imagine this atom is moving along, it comes along, it strikes the wall, it bounces off the wall, and ends up coming off this way. Well, we can see that that particle has changed its velocity. If it has changed its velocity, there must have been an acceleration. If there was an acceleration, there was a force acting on it. Where's that force coming from? Well, it's coming from the wall. The wall must have exerted a force on the particle as it bounced off. We can think about, remember when we were looking at impulse and we bounced that ball off the table? We figured out what the impulse was and then what the force was that the table had to exert on the ball. Well, we've got a very similar problem here. We've got an atom or molecule bouncing off the wall. That wall must have exerted a force on the particle. Well, if the wall exerts a force on the particle must have exerted a force on the wall. So we know that every time a particle bounces off the wall, it exerts a little force on that wall. And that's going to be true on all of these walls everywhere. As these particles, like think about a mole of particles, 10 to the 23rd, they're going to be bouncing off all over the place. So there is a force being exerted on the wall. The force per area tells us the pressure. So we know this gas must be exerting a pressure on the walls of the container. Well, what quantities do we think will affect the pressure? What kind of quantities in relation to the gas will affect the pressure? Well, we could certainly imagine that the more particles we have, the more often they'll be bouncing off the wall. If we had twice as many particles, we'll have twice as many collisions with the wall. That would give us twice the force, twice the pressure. So we would expect the pressure of the gas to be proportional to the number of particles. So we'll say that P is proportional to the number of particles N. Now, what else? Well, the faster the particles are going, the more they bounce off the wall, the more force they would have to exert, the more force they would exert on the wall. So we would expect that somehow the velocity of the particle or something like that would affect the pressure. Well, it turns out that what really affects it is the kinetic energy, and the kinetic energy is directly related to the temperature in Kelvin. So it actually turns out the pressure is directly proportional to the temperature. Again, it's directly proportional to the value of the temperature itself, not a change in temperature, not a delta T. So what units do we have to measure this temperature in? Kelvin. We have to measure it in Kelvin, not Celsius or Fahrenheit. Okay, what else? Well, imagine we were to double the size of the volume. If we doubled the volume, we would get half as many collisions on the wall per second. By making the volume twice as big, we would imagine just a particle going back and forth. It would bounce off the wall half as often. So what do we find? It turns out the pressure is inversely proportional to the volume. So the pressure is actually proportional to 1 over the volume. Well, great. Now, what else would it depend on? Well, there's a constant of proportionality we need to stick in there. And it turns out that constant does not depend on what the gas is. Assuming the gas is an ideal gas, which is what we're assuming here. This is for an ideal gas. Remember I said we're going to assume we're looking at an ideal gas for the rest of the class, for the rest of this lecture. Assuming it's an ideal gas, there is no dependence on a different kind of ideal gas. In other words, is it hydrogen, is it nitrogen, is it oxygen, something like that. So, but we do need to stick in a constant of proportionality. Well, we can then write this as an equality and write this as multiplying by V. We write this as PV equals N. The constant of proportionality we write as a lowercase k, and I'll come back to that in just a second, times capital T. Now, we can also write this in a different form. Rather than writing it in terms of the number of particles, we can write this in terms of the number of moles of particles. So rather than capital N, we can write this in terms of lowercase n. If we do that, the constant of proportionality K is different by a factor of Avogadro's number, just like big N and little n differ by a factor of Avogadro's number. And that quantity is called capital R, which we refer to as the universal gas constant. And then times capital T, the temperature again. And there we go. Both of these are referred to as the ideal gas law. Great. Now, the values of these constants are K, which is called Boltzmann's constant, has a value of 1.38 times 10 to the minus 23 joules per Kelvin, while R, the universal gas constant, has a value of 8.31 joules per mole Kelvin. So we notice the difference is this factor of moles. If you take 8.31, divide by Avogadro's number, you get 1.38 times 10 to the minus 23. Okay, very, very good. Let's stick some numbers in here. Let's imagine we have 1 cubic volume of an ideal gas. So say 1 meter by 1 meter by 1 meter. So 1 meter cubed. And let's imagine it's at 1 standard atmosphere, so kind of like the air in this room, and at about room temperature, let's say 20 degrees Celsius. How many particles and how many moles are we talking about in that 1 cubic meter? Well, we know that little n we can solve for is PV over RT. P, 1 atmosphere, is 1.013 times 10 to the 5th Pascal. The volume is 1 cubic meter. R, 8.31 joules per mole Kelvin. T, 20 degrees Celsius. Can we use 20 or do we have to convert that? We absolutely have to convert it to Kelvin. Remember, temperature Kelvin is temperature Celsius plus 273. So 20 plus 273 is 293 Kelvin. Divide that out and we get 41.6 moles. Now, how many particles is that? Well, 41.6 times Avogadro's number will give us the number of particles. That is 2.50 times 10 to the 25 particles. Now, just notice we're talking about a huge number of particles, 10 to the 25 particles. That is a huge number. It is very, very difficult to solve any kind of problems looking at all individual particles. It would be impossible, basically, if we've got that many particles. So what we need to do is kind of look at averages and things like that, which is why we're using things like the kind of the average pressure and the temperature and volume, things like that. We're not looking at what's going on with any individual particle, but what's the whole system doing. Okay, great. Now, what I'd like to do is go back to the ideal gas law and look at 3 different ways of changing these quantities, of 3 different processes that we might perform on a sample of an ideal gas.